This conference will now be recorded.
Everybody hear me? Okay. Yep. Awesome. All right. Let me see. Okay. So we are now on day 4, and here's a photo of extensive rime on a tree near the northern extent of the boreal forest, photo taken by Matthew Sturm. And outline for today, first we're going to talk a little bit about class logistics, again checking in on the schedule, some updates on first homework, including what you put together for the conceptual sketches and questions. Then we're going to jump into all the aspects of the snow surface interface. So on Wednesday, we're going to dive into what's inside that snowpack, which has been a white box up to this point. But today we're going to really talk about the interface. What is the point where the snow interfaces with the atmosphere above it? We'll talk about snow surface temperature, albedo, and about turbulence and how that's parameterized in models. Before we jump into that, let's just go through logistics I do at the beginning of every day. Let's see if this will work. Hello. All right, so it's amazing with a 1-month class. After today, you'll already be halfway through this entire course. How are people doing on the homework with the actual modeling and coding and making graphs? So people feel happier if I move it back to Friday for due date? Yes, is that a thumbs up? Yes? Okay, do you want me to also move the next one back to Friday as well? Is it just easier having them do Friday? Yes, okay, so I'll move both of those. Note that there's, I always thought the quarter system was fast, and then I started doing CUAHSI classes and make the quarter system seem long and luxurious. So I also recommend, in addition to doing that, make sure you start reading 2. 1 week from today, critique of reading 2 will be due. Reading 2 is a little bit less dense than the first reading. And then 2 weeks from today, your reflection will be due and your final presentation. So where are we? Just an announcement. If you're interested, basically what we've done in the snow community is trying to set up ways that everybody can access snow modeling, snow remote sensing, and snow field experiments. I mentioned earlier in the class the CUAHSI Snowfield School. There's a partner one run in Europe, so the deadline to apply is October 20th, and this year we run in Col de la Tourette in France. I taught in that school 2 years ago in 2018. It's an absolutely gorgeous location, and they will feed you way better food than we will feed you at any of the US snow schools. It's in France, so of course it's good. All right, so I encourage you to apply if you're interested. All right, thank you to everybody who has been posting questions on the discussion and sharing things on HydroShare. Thank you also everybody who's sharing their video. I really appreciate seeing all these small heads on my screen. It makes me feel less alone speaking here. The critiques are partially graded. I went through and looked at them all. I still need to enter all of the numbers. My goal is to do that tomorrow, so you should get feedback on your first writing critique before your second writing critique is done. Quick perusal, they all look good. There wasn't anything I was worried about. Homework 2 is in the debugging phase. For some reason, Suma kept crashing on me this morning, so I did not post homework 2. Homework 1, it seemed to run fine, so I'm not sure what went wrong with homework 2, but it should be up by Wednesday. That's the goal. The reflection is posted. You'll get 5 points just for giving me some feedback. Basically, this is still a work in progress, so if you just give me 1 page of your thoughts at the end of the quarter, I greatly appreciate that. The presentation assignment is also posted. You can decide what you want to present on. Basically, I want you to state by a week from today just what your general idea is and who you want to work with. You'll need a partner or 2, ideally groups of 3. You can decide whether logistics and interests are better to partner with people at your local institution or somewhere else. Ideally, it's, you just need to talk for 8 minutes, allow 2 minutes for questions, and you'll see as you go through these modeling homeworks that there's more examples and things you can do than you possibly have time for. So just pick something that looks interesting to you, check it out, and then share it with the group. And we will be grading each other. The rubric is posted, and we fully all understand your time limitations, right? So think of it as just, you know, one more extension on a homework, one more piece of the homework. All right. And any questions on any of those logistics? Sound good? All right. So your second reading is one of the first large model intercomparison studies, which was called the PILPS, and I forget exactly what all the letters in PILPS stand for, was a paper written by Drew Slater in 2001. Drew Slater was really essential and important help in the very first snow modeling class I ever put on. He's done a ton of modeling for both snow and of permafrost and in climate models. And he was in charge of really doing the evaluation of why were all of the different land service models in the PILP study totally different. So the idea, what you're looking at in this paper, is that there were a whole lot of models out there at the time. 21 all participated in the study, and all basically could make a snowpack. So you see here's a picture of 21 models. They all, you know, snow starts coming in November, disappears sometime in the spring. So they all could make snow, which is good. There's lots of spread in the models. Some of them consistently melted earlier, like the Shiba model. Some of them consistently melted later, like the SPS model. There was a fair bit of divergence during early or midwinter onset of melt. You can see that sort of in November, they're all matching, and then they all diverge right here in the spread circle. And then Drew describes in the paper that differences can be explained by model structure, model parameters, parameterizations. Specifically, he talks about albedo, how they handle fractional snow-covered area in their grid cell, thermal conductivity in the snow, emissivity of the snow, density of the snow, and aerodynamic formulations. So today we will be talking about 3 of these processes. You can understand them better, and then you can look at how they're affecting the different models in this paper. Before I jump into your questions here, any questions about the reading assignment? Similar to the other one, there'll be a few questions, not as many as the last time, because I know you're already also doing programming at the same time. Just asking you some questions about the paper and what you observe and thoughts you have on it. Any questions, just logistics wise? All right. So here are, I made you ask questions for your last one. And so there were a number of questions sort of about details about how SUMA works. A number of people asked questions about, you know, what is it about the Euler scheme, and what's the difference between an implicit versus an explicit Euler approximation. So I'll show you that in just a minute. Snow layering, we will really be diving into on Wednesday. So I'll try to answer these questions on Wednesday. We'll also, as we talk about solving for the snow layering, we'll also talk about the order of operations. And yes, Z is positive downward. We'll also talk about that more on Wednesday. And about how the definitions are handled for the various parts inside the snowpack, because I agree, that's all quite confusing. Just in terms of something you're gonna give me feedback on, last year, we did snow layering first, and then we did met forcing later. This year, I decided to start from the outside of the onion and go in instead of inside of the onion going out. You can let me know whether it's more preferable to wait to do this, or if you have any preferences. So regarding the stepping schemes between the Euler implicit versus explicit. So if you remember from lecture 1, we were talking about the necessary ingredients of a model. We talked about how some parts of the model, particularly the hydrology part, where you have some storage component in the subsurface or soil, it's a state variable, and that state variable, the amount of water you have in the subsurface, your stored water, determines your evaporation and your base flow. And so because the model fluxes depend on the state variables, you have to be careful with how you update them in time. So to see a little bit more of this, I made a new folder on the Canvas page called Time Stepping. And there's an article by Martin Clark in 2010 that he calls Numerical Demons of Hydrologic Modeling. And these are just some clips from the paper, which kind of looks like a lot of gobbledygook, but let's walk through it. So the first thing is, anytime we are solving any ordinary differential equation, which is what we have in all these models, over a time step from n plus 1, right, where our time step is delta t, really, if we're trying to figure out the change in something through that time, we need the complete integral of how it's changing every point along the way, right? We would want a precise and exact solution to do the integral over the time step. For most of the equations we have, that doesn't work, so we're solving them numerically. So there's two ways you could solve that numerically. And these are, again, just cut from the paper. If you're interested, you can read the whole paper in detail. So basically, the explicit or forward Euler scheme approximate the average flux by the flux at the start of the step. So again, remember, your evaporation depends on how much water you have in the soil, right? And so you take the amount of water you have in the soil at the beginning of the time step, and you calculate the evaporation, and then you move it forward. So basically, your change from n to n plus 1 is a function of your states at n. Makes sense? Now, the implicit or backward Euler scheme uses solely the flux at the end of the time step. So it calculates, okay, if something changes, how much water do we have at the end of the time step? And then it uses that to calculate the flux over the prior time step. Both of these, you'll see this O delta T at the end. These both have basically errors or uncertainty of the order of your time step. You can imagine if you're taking much bigger time steps, you have problems. So an example might be if you have a lot of water in your soil at the start of your time step, and you take a really big time step and you evaporate all that water away, right? You could actually think you're evaporating more water than you would as you're decreasing, right? Because as the water's decreasing, you're actually evaporating less and less each step. So you could evaporate too much water by approximating it in the front of the time step. So the short version of what is the difference between these, and it's not really the subject of our class, but there were a lot of questions about it, so I just wanted to give a little background, is that for the implicit Euler, even though errors end up on the same order, they're both the size of the time step, this one is much more numerically stable. It's a little bit trickier to program, so the reason why many models just have an explicit forward Euler time step is it's the simplest. Before I studied modeling, that's the way I would have done it, right? I said, okay, this is what it is, and I'm just going to approximate in the future without trying to guess the future and then go back and come up with the approximation. But the backward one is much more numerically stable, and you can more readily evaluate the error. And what you can do is you can have your model, and this is what the SUMA model does, look at what this approximate order of error is. And then if you are in a situation where it looks like there is a large amount of error, you can use adaptive time stepping. So instead of taking a big time step, you can say, okay, things are changing rapidly right now. We're going to take small time steps. Does that clarify a little? I'll show you one more picture on this. So this is just a picture from the paper I was just showing you. And again, this is for just a simple hydrologic model. You've got precipitation. This is unsaturated zone storage and then vertical drainage through the unsaturated zone. And you can see that the different colors, that these bluish ones are an explicit Euler and an explicit Hund, both with fixed time steps. So those are just going forward, where the implicit are taking the flux at the end of the time step. And then there's adaptive time steps in the black. And you can see that the two that are explicit, that are only using the values at the start of the time step, have unsaturated zone storage that jumps all over the place and has vertical drainage that spikes, whereas everything else looks much more physically realistic. So it's just you get numerical instabilities, and it's not a good idea to put it in your model. So that's what all that is about. In snow modeling, where it could come up is in the temperature updates and liquid water drainage and the stuff we're talking about on Wednesday. Most of the surface flux stuff is less critical on all this, just like we talked about that the sort of states aren't in it. The exception is with the turbulence flux, because the surface temperature is part of the calculation of the flux. And so if it changes, you'd want to use the implicit Euler to calculate updates in the surface temperature. Okay? People rolling their eyes at me. No? Okay. All right. You can ask more questions if you want, or you can say, all right, this model is okay, and this is just something I know I should check before I grab another model, or if I start seeing weird spikes, this might be why. Some more questions. People were asking more about specific parameterizations. How does turbulence come into play? We'll do that today. How does process parameterization work? I think we're going through, there's so many different processes and different parameterizations. We're going through lots of them one day at a time. We won't get through all of them. We'll just get through a subset of relevance to snow. What's the most difficult parameterization to represent? I don't know. Lots of them are very tricky. I think turbulence is pretty bad. After you see turbulence today, you can see if you'll go with me. Someone asked about the albedo decay rate. Is it linear? Is it not linear? It's actually something you can choose. You can choose one or the other. I'll show you that today. You can also, for your second homework assignment, you can choose to look at that. So we'll talk about albedo. Why is sublimation computed after computing the state fluxes? I'm not sure exactly why. I think one of the points of the paper was that, in addition to doing the time stepping scheme, a big choice you have to make in modeling is the order of operations. In which order are you going to do different things? And I think the idea with the sublimation was to do the energy flux first and then do the mass flux second. But I'm not sure exactly why. I would have to ask Martin why he made that decision. All right, so there were a lot of questions about spatial distribution. What are you actually doing here? There's a lot of dependencies. Those are going to have errors. They are, and it's hard to account for all the errors. I'm not sure this model has any lakes in it whatsoever. It does have rivers, and it's handled by a routing scheme. Basically, there's a time delay routing scheme moving water down rivers. You can adjust the width or thickness of each vertical column however you want. I'll show you a picture of that in just a minute. There were a number of questions about why is it okay to assume all snow moves up and down straight in a layer and not moving sideways through the snowpack. There are incredibly few snow models that allow water from one snowpack to another to move horizontally. There are some with blowing snow that will move the snow across the top, and we'll talk about that when we get to spatial distribution lecture. I've only seen a few studies where people really made lateral flow through the snowpack and they were not used in any practical or operational sense. It's very numerically challenging, and it's not something we have very good observations of. So usually, as in SUMA, we make the water go straight down the snowpack, and then it gets to connect subsurface in the soil. So water will move downhill to your stream once it gets to the soil, but it won't move downstream in terms of the snow. It won't flow in like an ice layer down the snowpack or anything. So just for a picture, so here you probably notice if you're looking at the setups in your model, it says things like GRU and HRUs. So GRU is sort of your watershed as a whole, and you can choose. We won't be in this class, but if you're using this further, other choices you can set up are, do I want grids? Do I want, lumped or polygons? How do you want to discretize? So you could set that up. So you can make it smaller or larger, however you want. You could distribute the meteorology however you want. And then you can choose how your columns work in your model. Does it just drain from the soil straight out to like a linear reservoir? Do you have an aquifer, and does that aquifer talk to aquifers next door? Is there just one? Are there two? And does the aquifer give water back to the soil above it, or can soil only give water to the aquifer? Again, that's all beyond the scope. We are going to stick with just a point snow model, get water from the top to the bottom of the snow and soil right underneath. We're not going to go as far as stream flow in this class at all. But in terms of just what the model does, there are options if you want to do anything further, taking it into runoff world. Any questions? To answer a few of your questions, maybe? All right. There also were a bunch about soil. Also, beyond the scope of this class, I would say that soil thermal conductivity parameters are not well constrained at all. I don't think supercooled liquid water will move. You can definitely have bedrock and just set it with 0 conductivity if you want, and it will make water just pool and go back up to the surface. All right. It looks like Chris went outside to get sunshine. All right. It's a beautiful day in Seattle. All right. So how does SUMA work? I think it's sort of a fascinating meta-analysis of how people think about models, right? How do we conceptualize them? So I'll just show you how your peers, I took names off everything, so nobody has to feel like super proud or super embarrassed by their picture. But these are just some different diagrams of how people interpreted the SUMA model as working. And it's interesting, some people, are minimalists and just wanted the big picture. Other people wanted to have, all the details. And I think it just is an example of how we think about things. And I think if you work on this for a while and ask you to draw another model 5 years from now, you'll probably draw a different diagram. So here's another one. This one has canopy airspace over the top of the mountains, but I really like the mountains. I think it's really cool. I like that one. And apologies, some of them I was just doing screen capture to get them in here. This one's all color coded. This one links all the temporal versus spatial versus vertical discretization. Some people like to use their computer, some people like to draw by hand. I usually like to draw by hand first. Some people cut and pasted the equations from the model. Not all the different parts. Again, just as good practice, it's a good way to help keep things straight and what you're doing. Some more with the equations and the layers here. Some people separated energy and mass balance into 2. I like this one. It has real trees in it, and then really healthy ground for being buried by the snow. There we go. This one I thought was interesting in that it was about like, how does a computer work? Step 1, what does the model do? Then what does the model do all the way through? I think some of us think more about what is the world we're trying to represent. Other people think, what are the flow path of the computer steps? Here's another one with, there's one monster giant tree here. I like the tree. All right, any logistics questions before we jump into surface temperature and albedo? See people laughing, smiling. Good diagrams. All right, well, you can go look at them all. They are also online if you want to see them with more time than I went through them kind of a mile a minute, just to give you an idea of different representations. All right. Okay. So let's see. Sunshine. All right. So, now let's go look at the top of the snowpack. So this is a photo from Jeff Deems taken in Colorado. What's the first thing you notice here in this photo?
Dust on snow?
Dust on snow. Yeah, crazy amount of dust on snow, right? So does SUMA represent dust on snow? It was in the paper you read. I see a thumbs up. Anybody remember that part? No, I don't remember it. That they had this lovely Met station. They simulated. Yeah, it doesn't. It doesn't have dust on snow. It's something that you might want to add, but right now there is no dust on snow. Okay, so here's a quiz. So we're talking both about, so this is sort of the interface, and there's two main parameters at the interface that are going to control how the surface of the snowpack interacts back with the atmosphere. So the modeled albedo is going to modulate our net solar radiation, right? That's how much of the sunlight is reflected from the snow. And we could tell from the prior picture, we had a bunch of dust on snow, and so we probably had a pretty low albedo there. And then the modeled snow surface temperature modulates both the net long wave radiation, somehow long wave radiation is lost from the snowpack to the atmosphere, and the near surface turbulent energy transfer. Okay, so you're playing with your homework that's due this week, and you're empirically modeling long wave radiation. So if you think we were empirically modeling both incoming solar and long wave radiation with a range of popular methods, and we kept all of our snow model parameters the same, which do you think leads to a greater uncertainty in snowmelt? How we model the long wave or the short wave? How many people are going to vote for long wave? Thumbs up for long wave. Long wave is going to make a bigger difference. Let's see, looks like we've got about 2/3. How many people are going to say short wave? Raise your hand. 1, 2, 3. We've got about 1/3 going short wave and 2/3 going long wave. The answer, like I did with the trees, is it kind of depends where you are. But most places, the long wave does have it. So here's a study led by Laura Hinkleman, and these are two Met stations in Yosemite National Park in the Sierra Nevada, which is a pretty sunny location. This is Dana and Tuolumne Meadows in the Tuolumne watershed, and she just wanted to know what impact does the uncertainty in long wave and short wave radiation have on snowmelt. So what you see here, the colors are different long wave sources, and the line style variations are different short wave sources. And so you can see that for this location, really the greatest variability in melt timing is due to which parameterization you pick for long wave. We kind of expected long wave to dominate the Pacific Northwest, so you would expect at Pascal's site in Umpqua that's going to be the biggest thing. Up here in Washington in general, it's the biggest thing because we aren't really sunny locations, right? Somewhere like Colorado where dust starts having a big impact, then albedo uncertainty starts making shortwave more important. But for most places without dust, long wave will give you more uncertainty. And what these all are just different empirical schemes, some of which you may recognize from what you're trying with the homework, like the Prada scheme and the Bertzier scheme. And then SYN is a satellite product. All right, so follow on quiz. So this was just everything else being the same. What we just did was our empirical estimates of incoming long wave, incoming short wave. Incoming long wave is more uncertain. If we add an uncertainty in both albedo and snow surface temperature, including emissivity of snow surface temperature, now does net shortwave, so that's incoming shortwave plus albedo, or net long wave have more influence on uncertainty in snowmelt timing? So how many people are going to shift and go for shortwave now? Anybody? Got about half. How many people are going to stick with long wave? Still going to be long wave. Got about one third now. So short wave's going up, long wave's going down. Is this just your psychology of I think Jessica's going to just change your mind, or I wouldn't ask another question? No, maybe. Okay. All right. So the answer to that one also is it depends where you are. It turns out that surface temperature can have a huge impact on melt timing. So this is work in progress by Nicoletta Cristea. So she took a hydrologic model, DHSVM. This is the same as the Vic model in terms of its snow scheme. It's like a sort of fine scale version of Vic. It has two layers. So here's a picture of it. I've been seeing the upper right. It has all the same energy balance we've been studying. And it has a bulk snow depth that's fairly deep, and then a skin depth that's a kind of shallow top layer. And all she did was she changed this thickness of this top layer. So your homework 2, what you're going to do in the scheme, a lot of you are asking questions about layers, is on Wednesday I'm going to talk about layers. And then for your homework, you're going to modify the layers in different ways in the SUMA model to see what they do to your snow melt. So what you see here is what you see is this skin depth, SD, that's the surface layer. She is varying it from 0.125 meters, that's 12.5 centimeters, down to 0.025 meters, so 2.5 centimeters. And looking at just how the surface temperature changes over the course of a day, and comparing that with observations. So the first thing you can see is everything looks slightly offset, and that's because the observations are instantaneous and the model is outputting at the end of the time step. So it looks slightly shifted because of an instantaneous versus averaged over an hour variable. So even in the fast response, it looks like about an hour behind. And what you see here is that if you have a really thick layer, just because it has a lot of thermal mass, it takes a while to heat up the whole temperature of that thick layer. If you have a very thin layer, then you heat it up more rapidly. So you have a much greater diurnal variation in the surface temperature if you have a very thin layer on the top of your snowpack. Now, what does this do to the rest of your snowpack? Does anybody care if they're not staring at the surface temperature of the snowpack? So it turns out that so the colors down here correspond to the same colors up here. So our really dark blue line is Nicoletta's really thick snowpack, and the lightest blue line is her thinnest snowpack. And so this is the model representation of the surface temperature. Down here is a model representation of the bulk snow temperature. And just like this red line here is the observations, the green and the red and the magenta lines are observations taken within the snowpack. So it's 25 centimeters, 50 centimeters, and 75 centimeters deep in about a meter deep snowpack, compared to the modeled bulk temperature. So you can see that the very thin surface layer is actually warming up during the day and transferring heat to the bulk snowpack. And the very thick one has a much colder bulk snowpack here because it doesn't heat up as much, and it doesn't transfer heat down into the snowpack. All right, so does that matter, right? If what we want to know is when does the snow melt and stream flow timing, how does that work? So so another thing, if we're thinking about the snow surface temperature, is the outgoing long wave radiation is going to depend how much we model of those, just our radiation lost to the atmosphere, on our modeled snow surface temperature and emissivity. So we've been talking about some model decisions that impact snow surface temperature. What else, which of these do you think might be most important, and what else might we want to be concerned about in terms of snow surface temperature? Any thoughts?
Wind speed?
Wind speed and turbulent fluxes, absolutely. We're going to talk about that next. Yeah, so the snow surface temperature will be modulated by turbulent fluxes, which will be controlled by wind speed, which one will have feedbacks on how much long wave is lost to the atmosphere. Absolutely. So it can be modulated by that. What else?
Tree or terrain shading?
Yeah, tree or terrain shading, right? If in your homework you're doing this week, you've probably seen very big differences between the under the canopy versus the open site in terms of how it's evolving. Anything else? I think those are big ones. I'll show you one kind of cool one. You see these observations in the red line here? So you see how it fluctuates really fast? So that's the turbulence. What does anybody think? See this is sort of the middle of the night here. Suddenly it's cooling, it's middle of the night. Sunrise is way over here. And so what's this little jump right here in the middle of the night? Why does long wave suddenly go up for, maybe, 20 minutes, half an hour? Any ideas?
Cloud cover?
Yeah, it's just a little cloud going over in the middle of the night. Yeah, so it's very sensitive to cloud cover as well. All right, so something else to think about is the emissivity also is going to matter. So these are some graphics from Dozier and Warren 1982. I put this paper if you're interested in the resources folder on the Canvas page. Note the emissivity varies as a function of wavelength and viewing angle. This is more important for interpreting observations than in terms of actually mattering for your snow model. Your snow model doesn't worry about wavelength or viewing angle. It just does hemispherical. This is how much my snow surface is losing heat. So all wave emissivity for snow is pretty high. So it actually emissivity will matter more for things other than snow. But you should not put it as exactly 1 in your model. It's another thing you see a lot of people will just say emissivity is 1. It actually should be close to 0.99. All right, so let's move on from surface temperature and the long wave part of the spectrum to albedo and the short wave part of the spectrum. So these are some slides from Jeff Dozier, and the definition of albedo is just the ratio of reflected solar radiation to incoming solar radiation. So that seems pretty straightforward. Most people had albedo in their diagram of how the snow model was working. Some nuances you might want to consider is that incoming solar radiation can be both direct and diffuse. So direct is like a beam, right? You got a beam of sunlight. Diffuse is what you get when it's cloudy, right? There's still plenty of light you can still see, but there's no beams and shadows so much. Albedo also generally increases when the sun is closer to the horizon. You get a lot more scattering off the snow. You probably notice if you try to drive late at night, you're getting more blinded than usual. And the term reflected really means reflected at all angles. So it's just going away from the snowpack. If you want a really super fancy model, you can reflect snow back to the snowpack if there's more mountains around it. Most of the studies I've read where people have done that show it to be a fairly small source of extra light. So why should you care about albedo? So one reason to care is that for the snow, we're really thinking about the fraction absorbed. So if you start with an albedo of 0.8 and you lower it by like roughly 20%, your albedo will go down to 0.6, and it doesn't look that big. But then your fraction of solar radiation that's absorbed is 1 minus the albedo, and it starts with 0.2, and then it goes up to 0.36. So it's an increase of 80%, or it's almost, if you're just rounding, it's almost doubling there, right? Everybody see how, and the amount that is absorbed by what looks like a small change in albedo can actually feel like a big amount to the snowpack. Okay, and the other thing is that solar radiation is generally, for a lot of locations, a pretty big number. So you're also multiplying this by a fairly large number that you're increasing by that amount. Okay, so what causes albedo to change? There was a question, someone said, like, how does it change and how are we parametering this anyway? Most of the studies and observations of snow albedo and how it changes have really looked at what is called spectral albedo. And this is because whenever we take measurements, we have to take measurements at a specific wavelength or specific range of wavelengths. Again, in terms of our model, we're just doing broadband albedo, how much is gone. But in terms of our measurements and observations, we are really looking at a specific range of wavelengths. So, so our spectral albedo at a given wavelength lambda, same definition, reflected solar radiation at lambda divided by incoming solar radiation at lambda. Now, because snow is made of ice crystals, and ice has different properties at different wavelengths, also because impurities like dust or soot affect albedo differently at different wavelengths. To understand physically what's going on, we actually need to think about albedo as wavelength dependent. Again, this is not in our model. This is what we know about physics and observations. So now we are looking at, so irradiance, watts per meter squared per micrometer here. So this is energy from the sun on the y-axis. And then as a function of wavelength in micrometers. So visible light, you see right here, is between 0.4 and 0.7 micrometers, or 400 and 700 nanometers, as you may have heard more. So we know how much there is just from the sun in extraterrestrial solar radiation. And then we know how some of that just gets scattered away by the atmosphere. So you see a lot of that's just scattered invisible light. You also see there's bands where water droplets or oxygen absorb a lot of the radiance in certain wavelengths that just doesn't make it to the surface. But then what's left is the blue line that would go hit our snow on a given face. Okay, so then what's going to happen to that? So once you know what wavelengths are going to hit your snow, then the spectral albedo, which is a function of wavelength, is a fundamental property of the material. It's going to vary with wavelength. It will also vary with illumination angle, just as I mentioned that the emissivity varied with illumination angle and wavelength, but less than the albedo, and with physical properties of the substance. The broadband albedo, this is the one we're trying to put in our model, is the convolution of both the spectral albedo and the spectral distribution of incoming radiation across all wavelengths. So basically we're doing broadband, we're integrating over everything. How much light at all wavelengths is coming in, how much reflecting all light at all those different wavelengths. Any questions so far? Making sense? Okay. All right, so now again, we're looking at the albedo as a function of wavelength in micrometers on the x-axis. And this is for clean snow. And so you can see that the albedo of clean snow varies with grain size. So tiny grain size, 0.05 millimeters here, has the highest albedo. Larger grain size at 1 millimeter down here has a much lower albedo. So here's just a picture of grain size. So here's your snowflake, and you can see the scale bar here is 0.1 millimeter. And then you can see some snow that's been sitting around, and scale length drawn here is 1 millimeter. So it's a factor of 10 larger than the one on the right. All right, so we know how the albedo of clean snow varies with grain size. And we just looked at two pictures through an electron microscope. So who can tell me what happens to our snow grains, size and shape, and hence their albedo with time after a new snowfall?
I think they become smoother and more aggregated.
So they're going to become smoother. In terms of size, so you did shape. What about size? They definitely become smoother and rounder, absolutely.
Snow grain size should increase with time.
Yes, the snow grain size increases with time. You notice that's why I was highlighting the scale bar on those two pictures. That they go up. So what is that going to do to albedo looking at this graph here? Our
That should
grain
decrease
Decrease.
albedo.
So if our grain size are getting bigger, our snow albedo, did somebody say increase or decrease?
Decrease.
Decrease, right? So draw an arrow, right? So grains get larger. We go from the blue line to the black line. And then albedo on our y-axis is going to go down. And the degree to which it goes down is going to be wavelength dependent, right? The biggest change is going to be right here in the near infrared wavelength. Any questions? Okay, so at a basic, what we're going to want to do in our model is have some parameterization. We may not keep track of all our grains and how they're growing and what's going on, but at a basics, we're going to have something that in days census snowfall, our albedo's got to go down by some amount. Everybody agree? This is something that all snow models have in some way. Now, the exact way they have it varies quite a bit, but everybody agrees on that. Now, clearly, you throw in dust or red algae or something else, and these are some pictures from McKenzie Skiles sent to me via Jeff Dozier. And here are some pictures, again, of going out with a spectrometer, looking at the reflectance. And you can see that the difference between clean and different sized grains is really quite small compared to the difference once you start throwing in really dirty snow or snow with red algae. That you start seeing that the impact of the dirt, the dust, and the stuff you put in the snow is bigger than the impact of just the grains of the snow. Everybody follow? So if these are not included in your model in some way, and they are in what you are trying to represent in the real world, you're going to have some problems. So here's from the paper you looked at. This was section 5.2.3. And this figure on the right is Senator Beck. That's the picture I showed you in the title slide from Jeff Deems. And I said, how did SUMA do here? And it turns out that you can run SUMA with various albedo parameterizations from different models. And they are very close to each other, but neither of them actually represents reality, which is the gray shading here, which is the observed snow depth, which is melting a lot faster because it has a bunch of dust in it. And the model didn't track dust. So something, if you want a research project to do, you might want to, if you're trying to model snow in Senator Beck, you probably need to add dust. If you're trying to model snow in Reynolds Mountain East, which doesn't get crazy dust events, you're probably fine with the existing model. So that's the one on the left. And you can see that both of them did fine. So again, a lot of it is thinking about what are the processes that matter where you are and which model actually has the most important processes for you. So having a variable versus a constant albedo decay mattered much less than the fact that just having dust on the snow. Any questions on this? All right, so on homework 2, which should be ready by Wednesday, you get a choice. This is not the required part, but it's something you could choose for your project if you're interested. So here is the state equation for snow albedo, which is the change in the albedo of the snow per unit time is a function of the density and the water content of the surface. It's a function of whether the snow has been refreshed, and then it's a decay rate of how much with time your snow is varying from some maximum and minimum parameters. You set what's the maximum minimum albedo it could be, how's it going to vary with time. You could have this variation with time be temporally constant, Doesn't matter about time of year, it always decays at the same exponential rate. Or you could have it be temporally variable. You could say, well, in the spring it's warmer and the grains grow faster, and so I think that the decay rate is faster in the spring than it is in the winter when it's cold and the grains stay smaller longer. Also, the SUMA model does not handle grains at all, but you could, if you really wanted grain size, you could use the French model, the crocus model, which if you go to the snow school, they'll teach you that one, or the Swiss model, their snow model, which I think is like Snowtran 3D. They have a couple of different names for it. Both of them evolve snow grains and calculate the albedo as a function of the snow grains. I don't think either of them have dust either. So again, if what you want is dust, you probably want to call up somebody who works in Senator Beck. All right. All right, so before we jump into turbulence theory, any questions about snow surface temperature or albedo? Okay. I'm going to close this one. All right. All right, so so for this one, I want to give special thanks to my former PhD student, Carl Lepo, who was a joint student between my group and UW Atmospheric Science Department, and decided that he really loved boundary layer meteorology and ended up really becoming, in the course of his PhD, a boundary layer meteorologist. He is now gone on to work in Germany and is doing all kinds of stable boundary layer mixing studies. I put the paper that this is based on is in the reference material interface folder. It's right with the albedo papers. And then also, if you're interested in anything, Carl put all of his turbulence code available on GitHub. Basically, what you're going to see is that you have a number of turbulence parameter choices in SUMA, none of which Carl ended up liking. So if you want different ones, you can go get them here. He also wrote some code to quality control shortwave sensors, which he said I should tell everyone about. So you're welcome to use his code. Okay, so so how many people have actually started getting some of their runs done at the Umpqua site? At least a few of them. Yeah, a third of you. So what do people think about what's happening with turbulence, winds, and rain on snow in Umpqua, Oregon? Why do you think our snow simulations at Umpqua were so very sensitive to how we adjusted the wind speed? Do you think everywhere would be that sensitive, or do you think we have a very particularly sensitive spot?
I would guess it's most sensitive at temperatures near freezing.
So the snow is going to melt, right? So the winds are more likely to melt the snow because it's really close to freezing. That's right. Do you think, what do you think in terms of like getting melt versus sublimation from the winds? Like we see melt happening here. What do you think about, like, if you're thinking about Oregon versus Colorado? What's a big difference if you're hanging out in the snow in the two places?
Relative humidity.
Relative humidity, right? So do you think so I'm going to finish for you and say we think it's more humid in Oregon than it is in Colorado. So do you think we're going to get more sublimation in Oregon or in Colorado?
Colorado.
Colorado's getting more sublimation, yeah. What might happen? What might happen to the moisture in the air blowing over the snow in a place like Oregon? So it's what, moist, very moist air. And a cold,
Condensation.
Yeah, condensation. And condensation releases a lot of heat. So actually, if you condense water on your snow, that's latent heat flux putting heat into the snowpack. So condensation on the snow can melt quite a bit. Sublimation will lose snow, you'll lose mass, but it will actually cool the snow surface quite a bit. So any thoughts about, has anybody noticed when you're playing with the amplifiers any particular sensitivity to wind in December of the simulation, December 1996? Not yet? Look at it, we'll come back to it. See if you notice anything particular in December and think about why, what might be going on in December that makes it so particularly sensitive right then. And if you want some more hints, I have an announcement from last year about there was a big event that happened then that might have something to do with it. Okay, so if you remember from the paper that had this monster table of all kinds of different processes you could put in, one of those processes you could pick was called a stability correction. And the model options say there are various formulations based on the Bulk-Richardson number, and you could choose from Anderson, Lewis, or Mart. So what I'm going to walk you through today is what exactly does that mean? What are these different choices? And how does it change how we model turbulence in terms of our snowpack and our land surface model? And when I say the word turbulence, I'm referring to both latent and sensible heat flux. Sensible heat flux is direct transfer of heat, that's heat you can touch, and latent heat flux is the transfer through water vapor. Most of the examples here, we're going to talk just about the sensible heat flux because it just makes the math a little bit closer, a little bit simpler because you don't have to worry about conversions of different formulations of vapor pressure and water content. And the parameterizations, actually, most models use the same for both processes. They use the same parameterizations that I'm going to talk about. Okay. So if we're trying to model surface energy balance of snow, we have to make a lot of model decisions. And we start by estimating the boundary conditions. We're going to parameterize our fluxes. We're going to come up with an equation that describes how much turbulence flux we think we'll have. And then we're going to specify some parameter values, and then we're going to solve it with a numerical solution. So typically, we inform the model based on observations. But you'll see that Delta SWE cannot be so helpful at sometimes in terms of diagnosing what's the best way to use the energy balance. So, so if you have a change in snow water equivalent less than 0, that means it's melting. So then we have information, and you'll see this is why we start with the Umpqua site, is that you see melt, right? The snow is isothermal, it's warm, it's right near 0, and it is responding by melting to most things you do at it. However, you can also, if the change in snow water equivalent is greater than 0, it's accumulation, and you can study how well you're parameterizing snowfall. But there's a lot of times where the snow isn't really doing anything, but the temperature, the internal temperature of the snowpack is changing. That's part of what I was showing you with Nicoletta's simulations where she changed the surface balance of the snowpack. So when you're trying to figure out what's the best way to do the energy balance, you probably want to pull in more diagnostic variables than just the snow water equivalent evolution with time. So here's a picture that just shows, here's your typical SNOTEL station. And you can see that over most of the time, the snow's just sitting there, right? It's not actively melting. And so if all you had to diagnose how well you were doing the energy balance was melt time packs, you would lose out on 83% of the time it's sitting there. So we can rarely test energy balance using just snow water equivalent. But if we include the surface temperature as a diagnostic variable, then we can start seeing errors in the energy balance more readily during times when the snow depth actually isn't changing. So this is a model representation of how snow water equivalent evolves in the SNOWTHERM model. So SNOWTHERM is a model developed by Rachel Jordan that has snow physics very similar to SUMA and has like over 100 layers. It has lots and lots of different layers in it. And here's what you can see in terms of, so basically what Carl did was he wanted to know, okay, given that a lot of our long wave schemes don't work really well and a lot of our short wave schemes aren't so great, what if we just bias them? What happens to our snowpack if we put in more energy or less energy? And you can see that this responds first and through most of the winter by raising or lowering the surface temperature from a baseline. So this is just change in surface temperature from a baseline simulation without perturbed energy balance. And so you can see that this is actually, quite helpful over a wide range. And then, of course, while it's melting, they all say that the temperature is 0, right? So 0 is when it's melting. And then the temperature stops being informative and the snow water equivalent starts being informative of how the snow is changing. So for much of the winter, we can use the surface temperature as a direct assessment of the snow's energy balance. Okay, so how can we use this information to help us better model the surface energy balance of snow? And so what we're going to do is we're going to use the surface temperature and direct measurements of the surface temperature to examine the sensible heat flux above the snowpack. All right, so what exactly do I mean by sensible heat flux or by turbulence? So hopefully at some point in your physics class, you saw some kind of picture that looked like this one up here. And you can see laminar flow on the left evolving towards turbulent flow, right? That these are eddies of motions of blowing some wind over a surface. You just get a bunch of mixing of turbulence. You'll also see if you like put milk in your coffee and lots of other fun things you can do, fluid mechanics. All right, so we got wind, and here you see down here, turbulence is mixing the air, right? Okay, so now how does that work for your snow surface? So here's our land or our snow, and here's the atmosphere. And so we've got a couple different conditions that could set up. So first Z, this is height above the surface here. I know in SUMA Z is positive down, but here we'll just draw it going up for a minute. So wind, we know the wind increases with height. We talked about that last week. And in this case, we're going to have a case where temperature decreases with height. So these are what's called unstable conditions. The surface is warmer and the atmosphere is colder, right? So we've got these turbulent eddies and they're bringing colder air from the atmosphere down towards the warmer surface. And so eddies are cooling the surface. And you can also see here is that as you take a piece of warm air up, warm air is lighter than cold air, and so it's positively buoyant. And so buoyancy is helping you with this turbulence and the mixing. The warm air wants to rise, cold air wants to sink. So not only do you have this mechanical mixing from the wind, but you also have the effects of buoyancy. So just to summarize, during unstable conditions, eddies move the warmer air up into the colder air. But we also know that this is rare over snow because snow is almost always the coldest thing around, right? Snow is almost always cooler than the atmosphere. Not always, but in general. Okay, so let's draw it the other way. So now during stable conditions, so here again, we have wind increasing with height, and now we have temperature increasing at height. So the coldest thing is right by the surface. So now we have warmer air over colder air. And so now what happens during buoyancy? So if we take a warm parcel of air and push it down, is it going to be happy? What is buoyancy going to be doing in this condition? How does
Is it
buoyant,
gonna try and,
say it again?
sorry, is it gonna try and keep that parcel of air in place higher up?
Yeah, it's going to resist mixing, right? The warm air due to buoyancy is not going to want to move down. So you're going to have, just due to stratification of warmer air being lighter than colder air, a resistance to mixing. So buoyancy is going to resist the vertical motions. And so we can define these competing processes in terms of something called the Richardson number. So the Richardson number is basically a ratio of the buoyant consumption of turbulence. How much does stability, warm air being over cold air, act against turbulence as a ratio of the mechanical generation of turbulence? How much wind is there that's really causing mixing and turbulence? And you can imagine that there, the wind is strong enough. It doesn't matter, how stable, you're going to just mix things through because you blew really, really hard, right? But if the wind's, somewhere in the middle, maybe not, right? Maybe that warm air might just go right over a cold, stable boundary layer. And so when SUMA says they have all of these stabilities parameterized as a function of the Richardson number, this is what it means. Okay, so for next Monday, you're going to be reading Drew Slater's paper. And so what Drew Slater found is that in looking at these 21 land surface models, the point at which they diverged the most was that they had very different representations of what is called the stability feedback. So basically, calm, clear night, there's radiative cooling, right? This is like the story of my car without the tree, right? It just loses its heat to the atmosphere, it gets cold, the surface temperature cools. As the surface temperature cools, the surface is now colder than all the air above it, right? So you have a high stability. With a higher stability, you're going to have buoyant forces reducing mixing, and so turbulence is going to be reduced. Without turbulence, you can't warm up that cold surface, and so it keeps getting colder. So, so this radiative cooling occurs at night. It also occurs in the polar winter all winter long. There's no sun, and it happens more over reflective surfaces that don't heat up during the day. So if you want to know like where this is an issue, here's a picture of where we would expect we would have snow and stable conditions over most of, this is just showing the northern hemisphere winter, and mountains and places with lots of snow are going to have this problem, which you can see that in terms of a climate model trying to represent what's happening over the Arctic. If you can't get this right, you're going to have some problems with what's happening in the Arctic in the winter. So again, here's a picture of stable conditions. You have warmer air and colder snow, and you generally would have a small net gain of energy to the snow, right? Warmer air should warm that snow up a little bit through some turbulent mixing. However, when you get very, very stable conditions, so now the air is much warmer and the surface is much colder, this is where models actually get confused on what they should do. And so models will either decouple, so they'll basically say buoyancy forces win, we're going to turn off turbulence, that is just so stable that these things aren't going to interact anymore, or they will continue some turbulent exchange. Everybody follow? Yes? Okay. Okay, so this choice turns out to be made very, very differently by lots of different models. So there was a very large range in the simulated sensible heat in all the different models in the intercomparison project. And this led to very large range of the simulated surface temperatures. Particularly in the middle of the winter, you could see ones here that didn't allow any mixing and just kept cooling all winter long. The site was far north in Russia, ended up with surface temperatures that were over 10 degrees C colder than other sites and than observations. We can see this other places as well. A paper by Holstag et al. In 2013, again, shows about a 10 degree C different in nighttime temperature in atmospheric models across the world. And if you look at global climate model CAM5 observations, it particularly over snowy regions has very large errors in simulated 2-meter air temperature. It's just these stable boundary conditions which occur over snow are really hard to model because people aren't sure how this balance occurs between the buoyant forces and the mechanical mixing forces in turbulence. So what Carl really wanted to know was, well, okay, we've got a choice of a bunch of different turbulence schemes. How can we evaluate them independent of the models? So basically in Drew's paper, he found this was a big key thing leading to differences between models, but the models did a lot of other things different, right? This was part of what that first SUMA paper you read was that, you know, if 10 things are different at once, it's hard to know which thing did which, and do we have 2 things that balance just right? So, so could he look only at turbulence schemes independent of the land model and see how they perform during stable conditions? So in this case, what he used were direct observations of the surface temperature instead of model evolution of the surface temperature. And then how can we explain from looking at that what, you know, works or doesn't work in terms of these stability schemes? So here are this is our parameterization plus our parameters. The first thing to think about whenever you are going into turbulence is to realize that different communities think different ways are up and down, right? That we in snow like to define a positive flux as heating the surface and a negative flux as cooling the surface, right? We want positive X to melt our snow and negative X to not melt our snow. So we tend to make Z positive down. That's what's done in the SUMA model, right? Because we want energy going down is positive. In terms of atmospheric science and boundary layer meteorology, they often don't care about the surface. They want to know what the surface is doing to their atmosphere, right? So their direction is the opposite way. So we start our formulation with a negative. It's always important to check depending where you're looking. Then our parameter then is a conductance term. So this is actually where most turbulence representations vary. So pretty much all of them agree that we should have more turbulence if the wind speed, so U is the wind speed goes up, we're going to have more sensible heat flux, more turbulence. And they agree that we should have some flux that is dependent on the gradient between the surface temperature and the air temperature, right? How much it changes. If they're exactly the same, we wouldn't expect, you know, however much the wind blew, it's not going to have any sensible heat flux. If they're very different and we have a lot of wind blowing, we would expect quite a bit of sensible heat flux. So, so typically when people are trying to evaluate how well turbulence makes, it's confusing. How much is there in air in the sensible heat flux, which is termed Q sub H? How much is there in air in the conductance, which is the parameter put in? And how much of the air is in the state variables, right? Do you just have the air temperature or the surface temperature wrong, and therefore you got this gradient wrong? So the goal here is to Carl directly measured surface temperature, directly measured air temperature, and then wanted to see, okay, now, and he also directly measured the wind. So now he said, okay, any errors we're getting in our model in terms of sensible heat flux should be caused by errors in this conductance term we're putting in here. So how well can we do that? So if you remember, I showed you when you turn on SUMA, you have 3 choices. You can go get the Anderson scheme, the Lewis scheme, the Mart scheme. Not in SUMA, but in a lot of other models, you can also select something called the Mononobikov scheme, which is supposed to be the best, but you'll turn up that I won't tell you the exciting results. All right, so each of these differ in how they are varying the conductance, which is, you know, how much heat flux is allowed per unit wind speed per gradient in the air temperature as a function of the Richardson number. And again, Richardson numbers getting progressively larger mean the buoyant forces are resistant mixing. So a large positive Richardson number means you have very stable conditions. You have very warm air over very cold air. 0 is just neutral conditions, neutrally buoyant. Okay. So these are what is called a bulk aerodynamic method. They're computationally simple. They're put in most global models. because they don't take a lot of time to compute. The full Mononobukov is an iterative method and takes a long time. Okay, so the Anderson method, you can see here, it's popular among hydrologists. It's in a lot of models. And you can see from the blue line that it completely decouples from the atmosphere. It basically says that if my Richardson number is greater than 0.2, I think that turbulence stops. No more turbulence. Now, the Lewis scheme was an attempt to match the Mononobukov scheme using the bulk Richardson scheme. So basically, they did a lot of numerical approximations and said, is there an easier way that we can come up with an equation that will kind of look like the Mononobukov, which is computationally hard? So you can see the green line and the pink line are somewhat similar to each other on the graph here. The MART scheme is supposed to represent variability in atmospheric stability. So what Larry Mart said was, when I go out, I see that, okay, even though it might be really stable over this patch of snow here, over here there's some trees and it's less stable. And I think that actually more mixing occurs everywhere because that less stable air is going to blow over this more stable air. And I should represent it by, changing this conductance term. Everybody follow? This is why it's not very popular to talk about all these parameters and parameterizations. You start getting into the weeds really fast. Okay, Mononobukov is very popular in atmospheric models. This is what boundary layer meteorology theory says is correct to use. But it's an iterative scheme, so it takes a long time to solve. Okay, so here is the conductance as a function of the Richardson number. Notice the Richardson number is a function of the wind speed and the surface temperature gradient, so it is related here. And so you can see the sensible heat flux, where you keep the conductance high, is going to just go up because you're getting stronger and stronger temperature gradients as you move out here. If it sets to 0, sensible heat flux is going to shut down entirely because you're just multiplying this by 0. And if you multiply it by a decreasing number, you can make the sensible heat flux fairly flat with changes. So what's a good idea? So one other thing to notice is that the Mononobukov scheme, if you look at what it's supposed to do in boundary layer meteorology, is supposed to be this little dashed line. In terms of most actual land surface models that say they use the Mononobukov scheme, they actually flatten it. So basically they just set above a certain level, they just set a constant conductance, which then just makes the sensible heat flux a linear function of the temperature gradient. This is not a numerical demon. This is a demon of details and modeling that sometimes people change their code without changing their paper that describes their code. And if you see anything really weird, you want to get an actual copy of the code itself. And that it turns out that people had just hard coded in, stop doing the Mononobukov and just make it constant. So it doesn't look like what you would think it was if you read the original paper. All right, so let's put that all together. And let me just check my time. So we've got, okay. My webcam's going. Webcam. Sorry, show the webcam. Yeah. All right, all the webcams went away. All right, I can't see you guys anymore. That's sad. Where did it go? Webcams. All right, I'll talk to you and not see you at the moment. You just have to yell at me. Okay, so let's put it all together. So, all right, so here are neutral conditions. Okay, so the wind increases with height. We're pretty sure about that. Here's a situation where the temperature, here is defined by theta, the potential temperature. For near the surface, it doesn't make much difference. Don't worry about it. If you're getting further from the surface, it starts mattering. So it's commonly used in atmospheric sciences. For neutral conditions, we can have good turbulent eddies, no problem, but the heat flux is 0 because there's no gradient, right? Okay, so now we start getting gradually stable. So temperature is increasing, we have warm air, we have decreasing conductance because now we have some stability, buoyancy is reducing mixing. So the Richardson number is about 0.1 here, but it's not too high. Warm air is mixing down to the surface. Now, very stable conditions. So here's this picture. We have a very sharp gradient of the temperature with height, and the atmosphere may decouple. We're not sure. Are we going to get, if we have decreasing conductance, we expect again there to be less mixing. So let's look at some observations. So here is a place I like to hang out. This is Snoqualmie Pass. It's right where I-90 goes over the Cascades. It's near a ski resort. Here's our weather tower. Here's our sonic anemometer measuring turbulent flux here. Here is another site. What I've learned doing this, if you have one sonic anemometer, you are not, you can't pull your weight in boundary layer meteorology at all. So you need to go find some friends who have 100 sonic anemometers. So this is the shallow cold pool site, which is in northern Colorado in the prairie. And this cracked me up because they told me this was complex terrain because it has little gullies in it. And everywhere you see a little yellow pushpin here, they have an eddy covariance tower with a sonic anemometer. And then here at the center, they have a very tall one with a number of 1 meter observations, 10 meter observations, and 25 meter observations. We're going to be looking at the 10 meter and the 1 meter observations here. Okay, so let's look at the 10 meter observations first. So how well does the modeled sensible heat flux match the observed sensible heat flux as measured by the sonic anemometers? So, so what do you notice here? I think, and I'll see if I can get the webcams back. Show all webcams. Yeah, there you are. What do you think? Good, bad, otherwise? You can't see anymore because when I pushed this, it went back to something else. Darn computer. Okay, I can't look at my screen and see you at the same time. What do you think? Nobody wants to talk.
It looks like most are biased. And that it looks like most of them are biased, and then the Anderson method has the smallest overall residuals.
You know, what's interesting is that the Mona-Nobokov one is actually the least biased overall. It's wrong at any given point in time, but overall, it's very good on average. You see that? So the numbers are the overall biases. The Anderson kind of looks closest to getting a shape that kind of looks like observations, right? It has the next smallest bias. It's the one that shut down entirely. So the first thing is the biases aren't that bad, but they're often caused by compensating errors, right? It doesn't seem to be getting the physics right or getting the right answer for the right reasons. And remember, we talked about we would expect, so here are just plotting the sensible heat flux and the observations, and the red line is the average with sort of a color bar of what we got, is what we would expect, right? That at very low gradient, we would expect not much sensible heat flux because there's no difference in the temperature. We'd expect some sweet spot where we got a pretty good sensible heat flux, and we would expect somewhere where it just became too stable and we stopped getting so much. You also see the scatter is pretty crazy. So again, small, the temperature gradient isn't large enough to cause it. Large, the atmosphere may decouple from land. In the middle, we would probably get the largest sensible heat flux. So at least on average, the observations show that. In terms of all the model schemes, they actually don't get that basic relationship. The simulated sensible heat flux really lacks this peak relative to the air temperature. It also, we notice that in our observations, we see what Carl calls counter gradient fluxes. So this is where the surface is colder than the air, but we actually see cooling happening towards the surface. So we'll talk about how that might happen in just a minute. So now wind shear and turbulence regimes. So now let's look at the wind speed in meters per second as a function of the sensible heat flux. And this is a really nice paper if you decide you want to become a boundary layer meteorologist by Jilun Sun, 2012, where she defines turbulence intensity from low to high is a function of 3 different regimes. So there's regime 1, a wind speed threshold, regime 2, and then regime 3 that you can see our observations fit into pretty nicely. Here's regime 1, here's regime 2. And the threshold really is where above this, you start getting a lot more mixing per increase in wind speed. The idea is regime 1, the eddies from the wind shear are too small to really reach the surface effectively. Regime 2, the wind shear and the wind speed is strong enough, you get large eddies, you're getting much more effective flux at higher wind speeds here. And the increase with further wind speeds is much steeper than at the lower wind speeds because you're having bigger eddies happening. Now what's up with regime 3, right? This one looks a little bit crazy. What's going on up here? And this is pretty cool from Jilun's papers. Okay, so this is why boundary layer meteorologists need at least 100 sonic anemometers. So it turns out that what we tend to do as land surface modelers is we measure flux at like 1 point somewhere near the surface. And this instrument costs $50,000 plus. And so if we have one of them, we think we're doing really well. What you see if you've got a whole bunch of them is that you see that actually you can get turbulence that starts higher than where you would typically measure. And so these are atmospheric waves that are actually propagating distortions in the atmosphere and causing turbulence near the surface that aren't measured in your lower level winds. And these just sort of don't fit the norm, but can still cause very large sensible heat fluxes when they occur. This is, you can see the energy propagating from higher in the atmosphere down near the surface. The only way you could ever hope to get this is to have a really high resolution, high quality atmospheric model coupled to your land surface model. We do not have this. We would not expect our model or any of our parameterizations to get step 3 at all, anywhere, anytime. So how are we doing? Nobody's got step 3. We didn't think they would. If we take this red line and we repeat it across all of these different parameterizations, you can see that this regime 1, they're all okay, but regime 2, they don't really agree on the slope of the observations. Also, they don't really agree well on the transition point, when you change from the shallow to the steep slope. Regime 3, again, we didn't expect it to get in the first place. The Mononobukov one, remember, like, is no longer really trying to represent turbulence. It just got capped at a constant value, and that's what it's showing. It's just showing constant sensible heat flux. All right, so in the interest of time, I am not going to go into the details of all 3 of these because the short answer is none of them worked very well. An interesting part is these counter gradient fluxes were observed in approximately 30% of all stable observations. And why we would get them is really just because of the heterogeneity of the surface. Again, what we tend to measure, again, we aren't getting the atmosphere up above, propagating waves down. We also aren't getting the land surface all around. So what you see out here is this is a plane that's run by the University of Washington Applied Physics Lab. It has a visual camera and some IR cameras. We're flying around near Snoqualmie Pass. And you look down and you can see, as you guys would all know and expect, that look, trees are a lot warmer than snow, right? By 10 degrees C. You can see this is our little spot right at Snoqualmie Pass. There's a ski resort over there. That roads are even hotter than trees, right? We have some really, right above our cold 0 C snowpack here, we have a lot of really warm surfaces. That here's the surface temperature of the snow, here's air temperature, and here's the temperature of the trees. Trees and the roads are all quite a bit warmer. And so we can get turbulence from adjacent areas causing problems over our point measurement. This is something I think someone mentioned in a question of, well, what if my snow is patchy and it disappears next to it? I'm getting warm air blowing over because of the patchiness. This is not in our models. It's not really in any typical snow models I'm aware of. So here's just a picture of how that might happen, is that we have a very stable boundary layer right near the surface, and then over the trees, we have this warm point and colder. And so depending where our measurement is of the flux, we could measure heat being transferred towards the ground or heat being transferred away from the ground. And this is why just having one eddy covariance observation, even though it costs a lot of money, can be confusing in terms of what is physically happening at your snow surface, right? Here are the trees, here's the mean wind, and you could see that things happening down here over the colder snow may be quite a bit different than what's happening up above where you're measuring it. All right, so just to conclude that and then let you all go on to the next thing on your day. Turbulence schemes as implemented in land surface models don't really do a good job resenting most regimes of turbulence. Most of them have fairly small biases, which means that they're not too terrible overall, but it's generally the result of compensating errors. There's a lot of work to be done in this area. And one large problem is just heterogeneity in the surface temperature and how that affects turbulence. And again, these are the ones in the SUMA model. If you're interested, you could choose to vary the stability scheme. Also, I just wanted to note that the paper that I posted ended up examining a number of other stability schemes that were recommended by reviewers in the boundary layer meteorology community that just aren't in most land surface models. So by just being more interdisciplinary, we could make progress in this field. And I'm now 1 minute over, but that's not too terrible. Any questions before we shut down and sign off? It's kind of a whirlwind tour of turbulence. Yeah. So it's my current vote for the hardest thing. I can't figure out what to do with turbulence, but I'm sure other things are equally hard. All right, we'll see you back on Wednesday, where we will go see how we put together our snow model insides with all the grains and the layers and insulation and thermal heat capacity, et cetera. Have a good afternoon.
Thank you.
Bye.